Great. Thank you everyone for joining us today for our webinar on NEC requirements for generators. A few announcements at the beginning. Audio for all attendees will be muted through today's presentation, but you can always ask questions at the bottom by clicking the Q&A button, or you can chat with us if you have other questions or issues using the chat button. We will save all questions till the end, but feel free to ask them at any time. Today's presentation is one part of a multi-part presentation that's available for CEU credits for engineers and electricians in Utah and Idaho. We are working on other states, but currently those are the only states we have approved through the state. We also will be sending out an email with the link to the recording of this, along with any additional documents or anything else that Craig brings up today. That should come out in 2 to 3 business days to the email which you registered for this webinar with. Otherwise, we'll go ahead and turn it over to Craig to present.
Thank you, Tyler. So the next two, I'm sure that we'll get a lot of people who are not interested in the codes and standards. After we get through these, we'll be on to some more webinars on generators of more general interest. But codes and standards are pretty important. Today is all on the National Electrical Code. As you know, the National Electrical Code is published by the NFPA, the National Fire Protection Association, and the NFPA has a number of other codes and standards that apply to generators, the most important of which is NFPA 110. NFPA 110 is a much smaller standard than the NEC, but the entire standard is on generators, whereas only a very small portion of the National Electrical Code is on generators. And we frequently are referenced to NFPA 110 in the code and vice versa. And so it's pretty important, but we are not going to have time to get into NFPA 110 today. So that will be next week. The majority will be on NFPA 110. We will also get into NFPA 37. Well, let me not mention the numbers, but we'll get into UL, we'll get into NFPA codes on gases and diesel and engines and all of that. So let's get started on this today. You'll notice in the upper left-hand corner it says Q1. So the way this particular presentation was done, it's the only presentation we have that's like this, is we thought back and said, what questions do we get from engineers and contractors and so on that have to do with the National Electrical Code? And then we wrote all those questions down, and then we grouped them into categories, and we came up with basically 17 categories. And so Q1 basically is question number 1, and when we get to question 17, then we're done with the presentation. Let's talk a little bit about where we find generators in the code. The NEC, of course, stands for National Electrical Code. NEC 517 is healthcare. There is some stuff in there on that. NEC 695 is fire pumps. The biggest sections are 700, 701, and 702. That's emergency life safety, legally required, and optional standby. So let me mention that when you come to me and you say, hey, I want an emergency generator, I just think, yeah, you want a standby generator. But if we're going to be more specific about that, and we actually have to when we're laying things out and doing pricing, there is a difference between an emergency generator, a legally required generator, and an optional standby generator. And it's very important that you know which type of generator that you have, because that will determine which generator you buy and which standards you have to meet. And we will get into that extensively here in the next hour, next 45 minutes. Interconnected electric power, we're not going to get too much into that because we're talking about standby generators. And then there's something called COPS, Critical Operation Power System, that was added after Hurricane Katrina, and that was their attempt to create a bulletproof standby generator system. And they kind of went overboard, and they went so far overboard that I don't think I've ever sold a COPS generator. It's very, very specific, but we'll talk about it a little bit as we go along. All right, let's talk about emergency systems. Emergency systems are loads essential for safety of human life. So if somebody could die as a result of that generator failing or not being there, then we call that generator an emergency generator. Now you have to be careful because a lot of people refer to all generators as emergency, and EPA has different terminology than the National Electrical Code for what emergency generator means. But in the National Electrical Code, it means that somebody's life is on the line. So what are some examples of that? Exit lights, egress lighting, egress elevators, fire monitoring and exhaust fans. As you know, the National Electrical Code is published by the National Fire Protection Association, and fire is always near and dear to their hearts. So if you need that generator to get out of the building safely, then that becomes an emergency generator. So pretty much any generator on a hotel is likely to be an emergency generator because they're using it for egress out of the building. And of course, healthcare. Now, all of healthcare doesn't require an emergency generator, just your life safety and critical circuits. Now, the second kind of generator that has different codes is your legally required standby. So both emergency and legally required are required by your local jurisdiction. You don't get a choice for whether you have a standby generator, it's required. So if you need an elevator in order to get out of the building, you have to have a standby generator. You don't get a choice. A legally required is a little less critical than emergency. So a legally required generator is one that could create hazards, hamper rescue, or firefighting. So elevators, you'll notice that we saw elevators twice, but if they're egress elevators necessary to get out of the building, they're emergency. If there are other elevators that are necessary for firefighting and to help with rescue, but they're not necessary for egress, then they might be legally required. Hazardous industrial processes, ventilation and smoke removal, sewage disposal. So water treatment plants, water supply plants, in many cases are going to be legally required because water is pretty important. And you don't want your sewage plant down in an emergency. Now, the final one is your optional standby. The optional standby has the fewest codes. In fact, optional standby generators don't need to meet NFPA 110 at all, but they do need to meet the National Electrical Code. And this says you don't need a generator, but you would like to have one. Examples: laboratories, radio and TV stations, data centers, food storage and processing like the refrigerator in a grocery store. You know, they want that up because they don't want to have to throw away all the food if it gets too warm. Internet service providers, communications companies, the gaming industry, you bet they have standby generators. Process industries, restaurants, lodging, retail, grocery chains, banks, all of these people would be classed as optional standby, even though many of them are pretty important. For instance, online banking. You don't want to have your online banking down because there's a power outage. So typically they will have standby generators. Question 2, what are the key codes and standards for generators? Well, these are ones that we're going to get into next week. But you have NFPA, and NFPA publishes more than the National Electrical Code. They publish many other standards as well. The International Code Council, CSA in Canada, UL in the United States. Intertech is kind of a substitute for UL. One of the bigger players now in generators is the EPA. And then you see some other organizations down there. This shows you some of those standards, and in the bottom we'll look at just the NFPA standards. 20 is on fire pumps, 37 is on engines, 54 is the fuel gas code, 58 is LP, which is liquefied petroleum. 70, of course, is the National Electrical Code. That's standard 70. Then 99 is healthcare, and 110 is the big one, standard for emergency and standby power systems. All of those really have some bearing upon the proper design and installation of a generator. And so we will get into those next week. Underwriters Laboratories, when I got into this business, you didn't see many generators with a UL label. And they're still, like motors typically are not UL listed, but generators are, and these days you must have a UL sticker on your generator. If you don't, there's a good chance that the authority having jurisdiction, in other words, the fire marshal or their local inspector, is not going to accept that. And if you don't have a sticker on the generator, it's pretty tough to get one on there because it actually has to go, if it's not built to UL, then you got a real problem. If it is built and you have to apply the sticker, you can't just do that in the field. You'd have to have a custom UL inspection or send it back to the factory. Transfer switches also have a UL. Engine generators are 2200, transfer switches 1008. That's only for low voltage, by the way. And then you've got your panel boards, and the tanks have their own standard. Here's different articles within the NEC. And you can see there's quite a few. We will get into those along the way. And here are more cross references in the NEC. So let's get on to question 3. What is a generator? Well, there is actually a definition for a generator in the code. It is a prime mover, that is an engine, and an alternator. Now, why would they say that? Why not just say a generator? Well, it turns out that these are kind of two specific pieces, and they don't need to be the same size. As you know, if you were in on our sizing seminar, it is very common to oversize the alternator. We oversize the alternator for 2 main reasons. The first is voltage drop. So if you're trying to start a large motor, or you're trying to start an elevator and you've got voltage drop limitations, which we always do, it may be necessary to oversize the alternator in order to be able to support the voltage and have a lower voltage drop. You don't have to oversize the engine, just the alternator. And I would say, and I'm guessing here, but I would say maybe 25%, and maybe even a little higher than that, of the generators that we sell have oversized alternators. I talked to one of our salesmen this morning, and the only conversation I had today, and we're specifying a generator with an oversized alternator. In this case, it's for harmonics. So an oversized alternator may be necessary to control your harmonics, and that's particularly important with variable frequency drives. So you remember, the engine provides kilowatts, the alternator provides volts and amps. So if you need kilowatts, it's got to come out of the engine. If you need volts and amps, it's got to come out of the alternator. Saw one time somebody said, well, let's buy a 200 kilowatt generator with a 250 kilowatt alternator, then we can get 250 kilowatts, right? No, that's not right. You can't get any more kilowatts than the engine produces. But if you're looking at voltage drop or harmonics, then that has nothing to do with the engine. That has to do with the alternator. Now, there are 3 types of wires, and one of them is your service entrance, one of them is feeders, and one of them is branch circuits. So feeders, and this is out of NEC 100, which is the definition sections of the National Electrical Code. A feeder is all circuit conductors between the service equipment, the source of a separately divided system, or other power supply source, and the final branch overcurrent device. Now, a branch circuit is one that actually feeds the actual load. It goes to a motor, it goes to a receptacle, it goes to lighting or whatever. That's your branch circuit. They feed the loads. And then the service is the utility. It's where you connect into utility. Anything between those two is a feeder. So basically, between the service entrance and the panel board would be a feeder. Now, all generator cabling is a feeder. It is not a service. Why is that? Well, let's look here. NEC 100, again, this is the definition section. It said the service is the point of connection between the facilities of the serving utility and the premises wiring. The definition of service was modified in the 1999 code to state that electric energy to a service can be supplied only by the serving utility. If electric energy is supplied by other than a serving utility, the supplied conductors and equipment are considered feeders, not a service. So this is a common point of confusion. People say, well, the generator, that's just another service. That's another place to get electricity. Well, that may be true, but as far as the National Electrical Code goes, it is not a service. The service is strictly the connection to the utility, and anything having to do with the generator is going to be feeder rules, not service rules. Okay, generator requirements. Question 4. Here's our 4 kinds of generators, and it kind of is interesting to me that every time a National Electrical Code revision comes out, they change these definitions. If it is an emergency generator, the generator must have adequate capacity and rating to safely carry at one time the entire load connected to it. And you'll notice, what does that mean? Does that mean if you have 3 motors and one's a spare, that the generator has to provide enough power for all 3? It used to be clear. It's not clear anymore. And it kind of irritates me that it seems like every time a National Electrical Code comes out, they make it worse. But at any rate, I'll quit complaining about that. What we would say is you just need to safely carry at one time the load that's actually connected to the generator and running. And so we would not put the spare in that. NEC 701, 702, this is your legally required and optional. Notice that they used to be entirely different and now they read entirely the same. They say it used to be with Article 220, that's the article when you build your house and you go through there and say, I got this many square feet, I'm going to have this many receptacles and all that, and it tells you how big your service needs to be. That's a terrible way to size a generator. But because you're going to get a way oversized generator, and you can imagine if you have a service on the outside of your house that's 200 amps, but you may never pull more than 30 or 40 amps in your house. Well, going with Article 220 is a terrible way to do it. But it also says by another approved method. What does approved mean? Well, that means that your inspector is okay with it. And then, of course, there's the healthcare facilities. And they make the most sense of all because they say you need to size it to meet the maximum actual demand likely to be produced. Well, gee, now that one actually makes sense. I wish they would have said that same thing on the others. Question 5, how quickly does a generator have to start up and transfer? Well, if it's an optional generator, you don't need it there at all, so they don't care. If it takes 6 days for it to start up and transfer, that's fine. You may not be happy with it, but the inspector doesn't care. If it's an emergency generator or a fire pump or critical or life safety loads, which of course would also be an emergency generator, it's got to start up in 10 seconds. And mostly when you hear people say, how quickly does it need to start up, they'll say 10 seconds. But that is actually only for those emergency generators and fire pumps. If it's a legally required generator, you have 60 seconds to start up. Now, let me mention one thing with regard to the 10-second startup time. All generators cannot start up in 10 seconds. Typically, a diesel generator is going to be able to start up in 10 seconds. Natural gas, all the smaller ones can, but the bigger natural gas generators many times cannot start up in 10 seconds. And so you need to make sure that you talk to the manufacturer if you're going to use one of these in an emergency application. I can tell you this, that all generators that Generac makes, whether natural gas or diesel, not only will they start in 10 seconds, but we will guarantee that we can start 2 of them and parallel them in 10 seconds. Question number 6. By the way, that's Generac. Don't expect other manufacturers to be able to do that. And if you're speccing a generator and you're speccing a 500 kilowatt natural gas generator, don't just anticipate that it's going to be okay. You better put that in your spec, that it has to start up in 10 seconds. Otherwise, you may be unhappy with the result. Question 6 is an easy one. One transient limits are required by the NEC. In other words, how much voltage and frequency drop can you allow? And fortunately, the NEC didn't get in and try to mess this up. So they basically just said the transients should be acceptable to the load. I generally say that if you have solid state devices there, you should never allow more than a 15% voltage drop. If you only have relays, which is less and less common these days, maybe you can go to 20%. The generator is fine with 35%, no problem. But it's the loads that are going to have a problem when that voltage dips further. So that's just my opinion on the matter. What items affect the load transients? The size of the load and its characteristic, motor starting codes and starting methods, engine size and fuel type, and the alternator size. So if you're starting a big motor, you could reduce the voltage drop by going with a bigger alternator. Doesn't need to be a bigger engine, just a bigger alternator. Or you could go with a different type of starter on the motor. And we do both, depends on the situation. What alarms and instrumentation are required? Well, let's talk about emergency first. You've got to have a malfunction alarm. I think of the malfunction alarm as kind of the engine check light. You get that engine check light comes on and you're always unhappy because it's telling you something's wrong, but it's not telling you what is wrong. And all generators will have a malfunction light. In some cases, it's just a light or a buzzer and it tells you there's a fault, or an alarm. In other cases, with more sophisticated controllers, it will actually tell you what it is that's wrong. Carrying load, well, what does that mean? In general, that's on the transfer switch. And so if the transfer switch has a light that says you're in the emergency, or the, actually it's called normal and emergency, and it tells you which position it's in, that satisfies that. Battery charger failure and ground fault indication. We'll talk about ground fault later. Notice here that it does not say ground fault protection. We don't put ground fault protection on generators. If you've got a generator necessary to preserve human life, why in the world would you want it to trip because you've got a swamp cooler that has a ground fault on it? In addition, that's conditional. Basically has to be over 1,000 amps, 480 volt, before you actually need that. So ground fault indication, it just indicates that there's a ground fault. It'll have a light and generally an annoying buzzer, but it does not actually trip the generator. If we go down to 701, now this is your legally required, and notice that it used to not require ground fault indication. Now it's conditional, and in most cases it actually doesn't. NEC 702, this is your optional standby. All that has to do is malfunction and carrying load. Now that I've told you that, I'm basically going to tell you that I lied. And that is for this reason. If you have NEC 700 or NEC 701, the National Electrical Code only requires the alarms and instrumentation that we show there. But if you have an emergency or a legally required system, you must also meet NFPA 110. Now, we're going to talk in detail about NFPA 110 next week, but right now, let me just point you to this. If they want to make this difficult for you, so see where it says level 1? That's basically the same thing as an emergency generator. And there's a level 2, which is not shown on the slide, which is the same thing as a legally required generator. So now look at this. You've got to have an overcrank, you've got to have low water temperature, you've got to have a high engine temperature pre-alarm, high engine temperature, low lube oil pressure, overspeed, low fuel main tank, and so on and so forth. The left column over here says control panel visual. That's basically the controller on the generator. The S stands for shutdown, so they're saying overcrank you need to shut down, but low water temperature you don't. And then over here is your remote annunciator or your remote audible. And in the lower right-hand corner is a remote annunciator. They're pretty good. They're only, I'm guessing, like $400. So it's not a hugely expensive item. And they have lights for each one of these alarms in shutdown situations. So I told you some generators only have a malfunction light. Other generators will actually show you what's wrong, and the code actually requires that if it's a legally required or an emergency generator, not only do they have to have all these sensors there, but they have to show you which one of these things is causing the problem. And you can see for level 1, I have to have a remote annunciator somewhere, like in a hospital, it might be a nurse's station, or in a water treatment plant, it might be in the, or a data center, it might be where, you know, the guy sits that is looking at the screens that control the plant. And it'll basically just have an annoying piezoelectric buzzer here, and he can look at it. And so this light might come on and it'll say high battery voltage. Well, he may not know what to do about that, but can he always call somebody and say, hey, this thing is making a racket, and it says high battery voltage. What should I do about this? And then someone who is a maintenance person can come out and take care of that. Now there is a silence on here. You can push the silence and it'll turn off the annoying buzzer, but keep the light on until the alarm actually goes away. Let me mention one more thing here. If you buy, there are two types of generators, and I could say that in a lot of different indications. But in this indication, I'm saying that there are industrial generators, and then there are commercial and residential generators. Commercial and residential generators are not built for emergency. They're not built for legally required. They are only built for an NEC 702 optional standby. So they may only have a malfunction light on. I'm not saying they will. The controller could have more stuff, but it's only required to have that. And because of that, they may not even have these sensors in the generator, let alone be able to enunciate them. In addition, there are other differences, like a brushless alternator and a permanent magnet alternator and an emergency stop push button that are necessary when you get into an emergency generator, that are not necessary if you just have a generator on your house. So we get into trouble a lot of times. People will go out and they'll buy either a residential generator or they'll buy a light duty commercial generator, which are perfectly fine. They use those on all kinds of commercial buildings, 7-Elevens, places like that, but they cannot be used as an emergency or legally required generator because they don't have this NFPA 110 controller. And this is a heartbreaker. When somebody buys a generator, puts it in, the inspector comes out and says, well, where's the remote annunciator? And they call us and say, hey, we need a remote annunciator. And we tell them, there is no remote annunciator. You didn't buy an NFPA 110 control panel, and it's not available. You got to buy a new generator. And I hate telling people that, but I want to just make sure you understand that the generator that you purchase must be an industrial generator with an NFPA 110 controller if you want to use it in a legally required or emergency application. If you want to buy one of the light duty commercials, which we sell quite a few of, or a residential generator, no problem, but just don't use it in an emergency or a legally required situation. Okay, I've probably beat that to death. What are the generator signage requirements? You need to have two signs on a generator. One is located at the service, and it tells you that you have a generator and where it is. It also should tell you the generator type, as in diesel or natural gas. And then you have to have a generator grounding sign, generally where you have your neutral to ground bond. How many generator installations have these two signs? Well, I have yet to see one. So it is a NEC requirement, but most contractors don't know it's an NEC requirement, and most inspectors don't know it's an NEC requirement, so nobody does it. But it is a requirement, so I'm letting you know that. Disconnects. So we did a little sneaky on you here. Question 9 has 6 subparts, A, B, C, D, E, F. And so let's look at those. First of all, does the NEC require a generator disconnect? In other words, do you need a circuit breaker on your generator? Well, I can tell you this. We at Energy Management Corporation have never sold a generator without including a circuit breaker on it. Now, we would, if the engineer comes in and says, I don't want a circuit breaker, leave it off. We would do that if we were told to do that. But otherwise, we always include it. Now, if you don't want a circuit breaker, then the generator must have shutdown provisions, which is an internal and an external e-stop. And you really need overcurrent protection out there. And so the NEC, as you read it, just assumes that a generator has a circuit breaker. And so we put one on there. But you could get away without it, and a lot of people do that. B, what is the generator breaker's accessibility requirement? Well, in NEC 404.8, it says all switches and circuit breakers used as switches shall be located not more than 6 foot 7 inches above a floor or working platform. Obviously, the intent of this is if you have a circuit breaker, an average sized person has to be able to reach it so he can turn it off. And they decided that 6 foot 7 inches would be that level. So if you have a motor control center, if you have a panel board, switchboard, you can't have breakers located higher than 6 foot 7 inches. Well, it turns out that on a generator, you will often have a circuit breaker. You put and maybe it's 4 feet above the rails of the generator, and then you put it on a 3-foot tank, and now you're higher than that 6 foot 7 inches. So is that okay, or is that not okay? Well, it turns out that it is okay, because there's an exception there. It says switches and circuit breakers installed adjacent to motors, appliances, or other equipment that they supply shall be permitted to be located higher than 6 foot 7 inches and to be accessible by portable means. So with Generac, we've tried to reduce the level in the generator at which we mount those circuit breakers to try to keep them in a position where you can reach them. But it's still possible when you get a really large generator with a high tank, you may not, and that's fine. Is a disconnect required at the point of building entry? So typically we go from the generator to the transfer switch, and the generator is typically outside, and the transfer switch a good share of the time is inside. Well, you generally need a disconnect whenever you have a feeder that goes into a building in order to feed power there. However, with a generator, you don't need that because it is exempted. And you can see that for outdoor generator sets, they say that when the outdoor generator set is equipped with a readily accessible disconnecting means, well, there's that circuit breaker again, and the disconnect means is located within sight of the building, an additional disconnecting means shall not be required. So there are some jurisdictions in the country that actually want a switch or a circuit breaker between the generator and the transfer switch where it goes into the building. But thankfully, none of them are here in the Rocky Mountain area. And so if a local code requires that, that could be an issue, but it's pretty rare. But we have seen it, particularly in some of the bureaucratically intense cities. I'll just say that. What does within sight of mean? It means visible and not more than 50-foot distance. So you got to be able to see it, and it can't be more than 50 feet. We will talk about that a little bit more in a minute. Now, readily accessible means capable of being reached quickly for operation, renewal, or inspections without requiring those to whom ready access is required to climb over and remove obstacles or to resort to portable ladders. In the handbook, it clarifies that to say the definition of readily accessible does not preclude the use of a locked door for service equipment. So if you have a locked door, it is still readily accessible to those with a key. But if you walk in the electrical room and they are using it as a storage room, and there's a bunch of boxes piled in front of the switchboard, that is not readily accessible. Now, what if the generator is more than 50 feet from the building? Well, It says for installations under single management where conditions of maintenance and supervision ensure that only qualified persons will monitor and service the installation, and where documented safe switching procedures are established and maintained for disconnection, the generator set disconnecting means shall not be required to be located within inside of the building. So there is an exception for that. Cabling. Now, this is an important one. I'm talking to people all the time about this because you go out there, you look at a generator, and let's say the generator full load amps is 340. It very well likely may have a 400 amp circuit breaker on there. So people would say, oh, I have to have 400 amp wire, because they're used to the fact that the wire has to be the same size as the circuit breaker because the circuit breaker protects that wire. Well, that's true in many cases. It is not true for a generator. You have three choices. Number one, you can size the circuit breaker for you can size the wire according to the circuit breaker, or you can size the wire to 115% of the generator rating, or you can size the wire to 100% of the rating if the generator has overload protection. Now, all of our generators have overload protection. And so just to give you an example, let's suppose that you have a 500 kilowatt generator. The full load amps on a 500 kilowatt 480 volt generator is 752 amps. It's going to have an 800 amp breaker in it. Well, if you size according to 100% of the generator rating, then you can use two 500 MCM cables rated 380 amps a piece. So that gives you 760 amps, which is more than the 752 that is the rating of the generator. If you go with the circuit breaker, now you can't do that. You're going to have to go with either larger wire, and I've always assumed that if I use anything higher than 500 MCM, the contractor's going to kill me. Or you're going to have to go with another conduit, another set of wires. So this can save you a significant amount of money, and the copper prices are not ever going to go down. They continue to go up. So I recommend sizing to 100% of the generator rating typically. Question 11, this is separation of circuits, and I'm not going to get into this too much, but it used to be if you have one generator, but it supplies emergency loads and non-emergency loads, then you put two circuit breakers on the generator. And those two circuit breakers, you have to have two transfer switches, one for emergency and one for other. That's part of the code. And they have to have their own circuit breakers. Well, it used to be that we just put two circuit breakers together. Then the code came out and said, nope, we are not going to allow that. You must have metallic isolation between the emergency circuit breaker and the other circuit breakers, because if that other circuit breaker blew up, it could take the emergency breaker out. And so you have to isolate those two. So Generac met that by redesigning all their generators. And if you have emergency system and other loads, you'll have the emergency breaker on one side of the generator, and the other side of the generator will have the other breaker. So not only are they isolated metallically, but they're a long ways apart. If you have a generator that feeds a panel board or switchboard, and that panel board or switchboard then goes to some emergency loads and some other loads, you have to basically put your emergency circuit breakers in a separate vertical section from the other circuit breakers, and that's a pain, because you could have a 100 amp emergency circuit breaker, and it has to have its own vertical section. And I haven't seen, inspectors don't seem to know this, but I would be careful about that, because you don't want to have that rejected by the inspector. That was a new requirement. This is requirements for coordination. I'm not going to get into this in detail because engineers know all about coordination and other people don't care. That's an overstatement. But in any case, if you have an emergency generator or a legally required generator, it must be coordinated. And that means that, as you see in this bottom rung here, if you get a fault on that circuit breaker in the middle, that circuit breaker should trip before the main circuit breaker feeding the whole panel. Now, typically, number one, I consider a 100% rated circuit breaker and a generator to be a total waste of money. And I don't have time to get into that in detail, but let me just say that outside the generator, that's an 80% rated circuit breaker. When you put that 80% rated circuit breaker in the generator, and then that has been tested with the generator to UL at 100%. Now, LSI circuit breakers, I generally don't want to use LSI circuit breakers because they cost a lot of money. For, you get like an 800 amp circuit breaker, it can almost be the price of a car. It's just ridiculous. Biggest scam in the electrical industry, in my opinion, is molded case circuit breakers. And so I don't want to buy LSI because for the additional price of an LSI, I could have gotten a sound attenuated enclosure. However, if it's an emergency or a legally required system, sometimes you have to have the LSI in order to coordinate. And you don't want to try to do that after the generator is already on site. It's going to be much more expensive. So sometimes LSI makes sense if you have to have it for emergency or legally required systems. Grounding and ground fault, this is question 13. What are the grounding requirements? Well, we talked about this with transfer switches, but for those of you who may have forgotten or who didn't listen to that, we have 3-pole and 4-pole transfer switches. Now, I'm only talking about 3-phase right now. If you have a 3-pole transfer switch, then you have a neutral bus bar. And basically, the generator neutral is connected to the system neutral in that neutral bus bar. And so your neutral to ground bond occurs at the service. And you do not have a neutral to ground bond at the generator. Now, the generator enclosure still has to be grounded. You still have to have a ground wire in there, but you do not have that bond between the neutral and ground at the generator. That is at the service. And if you put another one in at the generator, then you have 2 neutral to ground bonds, and that's a code violation. So if you have a 4-pole transfer switch, then the neutral is switched. And because it's switched, then that neutral can never be connected to both the service entrance ground and the generator ground. So in that case, you're going to have 1 neutral to ground bond at the service and a second neutral to ground bond at the generator. This is very confusing, and a lot of times contractors are just not going to know this. If you put a neutral to ground bond in and you have a 3-pole switch, you have violated the code. And if you don't put the neutral to ground bond in and you have a 4-pole switch, you've also violated the code and you've caused some problems. Now, this shows the neutral to ground conductor right there. It's just basically a wire that connects your neutral to ground. You can only have one, and on any given system. Of course, if you go through a transformer, you're going to have another one, but on any system, you're just going to have the one and only one. You must have one. You cannot have only one. Now, we generally also require a ground rod at the generator, but you should also run your ground out to the generator and ground the generator itself. But if you have a 3-pole switch, do not connect the neutral to ground at the generator. If you have a 4-pole switch, then we must do that at the generator. By the way, if you wondering why would you choose 3-pole or 4-pole, this is in our transfer switch class where we went over it in kind of detail. And I'll just mention that generally you want to use a 3-pole because you don't ever want to switch a neutral unless you actually have to. But if you have multiple transfer switches, I would recommend that you go 4-pole on the same generator, obviously. If you have very high sensitivity, 0 sequence ground fault on the generator, then you need a 4-pole switch. And if you're using one generator to feed 2 buildings that have their own separate service entrances, then you have to have a 4-pole switch. All right, let's go on to question 14. Are generators required to have ground fault indication or ground fault protection? And they have to have ground fault indication only if they are 480 volts, 1,000 amps and more, and on an emergency system. So if you're in a non-emergency system, you don't necessarily need it. If it's under 1,000 amps, you don't need it. And if it's 12240 or 12208, you don't need it. So most of our generators are not going to have ground fault indication. And remember, we never put ground fault protection. We never trip the generator. We just put ground fault indication. And this gives you some more information on that. You can see that legally required does not require, ground fault indication and optional standby don't. The legally required, there is an exception there, but I won't get into that. This shows you a 4-pole transfer switch. And in this case, you can see that we have a 0 sequence ground fault indication. So current goes out here. This would actually be 3 separate switches, but we're just showing one phase. It comes down through here, and let's assume that there's actual fault where it goes to ground. Now, in order to get back to the generator, it has to go through here, and therefore the current goes through the 0 sequence, but it doesn't come back through, so this detects an imbalance and it will trip. If you used a 3-pole switch there, then this would just be a neutral bus bar. You wouldn't be switching that neutral. So now it would come out, it would go through here, then it would come down into your fault. But because with a 3-pole switch, there would be no neutral to ground bond at the generator, it would have to come back through the service. And when it came back through the service, it would go through this 0 sequence ground fault. It would trip your utility breaker. Then it would come back to the generator. The utility breaker would trip. The generator would not be able to see the ground fault because it came out through that 0 sequence, came back through the 0 sequence. It doesn't see the imbalance. So that's why you need your 4-pole. What are the code requirements for transfer switches? Well, this is generally pretty easy. It shows all the requirements there: automatic, approved, mechanically held, and so on. But typically you buy a good quality transfer switch and it's going to have all those things, so it doesn't tend to be ever a real problem. Remember that if you have emergency circuits and legally required, or emergency and other circuits, they each need their own transfer switch because those circuits have to be separated. In a hospital, you need 1 transfer switch for equipment, 1 for life safety, and 1 for critical. Life safety is basically your building evacuation in your hospital. Critical is your emergency rooms and your operating rooms. But they said if it's like a portable hospital, so it's less than 150 kVA, they will allow you just to have 1 transfer switch. And our final thing is fire pumps. I've always said that the way they wrote the section on fire pumps is they promised a free cruise to anyone who could write an entire section of code that absolutely no one could understand. And so we could talk for a complete hour just about fire pumps. So let me just give you a couple of the highlights. If you have a circuit breaker on the utility that feeds the fire pump, it must be set to indefinitely carry the sum of locked rotor current. In other words, it's a fire. They're never going to trip the motor. They'd rather let the motor, the fire pump, burn up than trip it. But that is not the case with a generator because you'd have to have a gigantic generator. So the generator generally just needs to be sized to be able to run that motor. It does not need to be sized for the locked rotor amps. We generally want the circuit breaker and the generator to be over 125% of the motor rating. And in the normal starting method, normally it says right here, the generator shall have sufficient capacity to allow normal starting and running. And in the handbook, it says on-site standby generators are required only to be capable of carrying the starting and running current, not the locked rotor indefinitely. So we generally have a normal starting method and a backup method, and the normal would be a VFD or a reduced voltage starter or a delta Y starter. And in that case, let me see if I can find it right here, the voltage dip is limited to 15%. That can be a real difficult situation, especially if you have a Y delta starter, to try to start that thing and maintain no more than a 15% voltage dip. But then you have the backup method, and that's always across the line. And in the backup method, you're not limited to the 15%. So you actually have to size your generator twice. Once on your normal method, that would be a reduced voltage starter or a VFD or delta Y or what have you. and then the backup method is across the line. It still has to start it, but it's not restricted to 15%. The ATS must be fire pump rated if the ATS is always supplied by the fire pump manufacturer, not by the generator manufacturer. So for instance, at Portneuf Hospital up in Pocatello, they have 18 transfer switches up there. We supplied 17, and the fire pump manufacturer supplied 1. And so we don't even sell fire pump rated transfer switches. We could get them, but we'd have to go to a fire pump manufacturer and buy them. And so generally they come as a package with the fire pump. Generator must meet the requirements of NFPA 110 level 1. In other words, it's got to meet all the requirements for an emergency generator. So that is all. I appreciate your time. I will turn the meeting back to Tyler.
Great. We've had a couple questions come in. Feel free to continue submitting them. First, how often is the NEC updated regarding generators?
Great question. So the National Electrical Code was first published in 1897, and it's updated every 3 years. So that's not with regard to generators, that's the whole code. But I have never seen a new version of the code come out in which they didn't change some of the generator sections. So as you know, the previous version of the code was 2017. The present version of the code is 2020, and the next code will come out in 2023. I guess I would be somewhat skeptical of the 2020 code, seeing how 2020 has gone so far. Okay, a little humor, but yeah, every 3 years.
Great. How do you connect a generator to common bus bars, which has main utility power and solar power supply? How will they operate interchangeably?
Yeah, so this is not an easy question to answer because it's going to depend on your system. For instance, if you go through a transformer, then you need to have a whole new neutral to ground bond. So let's say you have 480 volts and you go down and then you have a transformer that goes from 480 to 208, 120. You have to have a new neutral to ground bond on the 120, 208 volt side because it went through a transformer, which isolates your neutrals and your grounds. And in the case of a solar system, there are just so many different ways of doing a solar system that the only thing I can really tell you is you're going to have to look at the particular type of solar system that you have and look at the system connection diagram before you'll know how you can really connect that together. There's just not a simple rule that I can tell you. But typically, unless you have isolation in there, you're going to do your neutral to ground bond at the utility, and no one else would have a neutral to ground bond. All the neutrals would go to the neutral bus bar if it was going through the transfer switch. If it's not going through the transfer switch, then of course that's immaterial.
Is there any code reference for oversizing generators?
Nope. The code basically, there is the section that we talked about on how big a generator needs to be, and basically they're saying it either needs to be Article 220, which is your typical how you size a service entrance, or other approved method. And basically, we just size generators to be big enough to run the load. Now, so it can't be really smaller than what's necessary to run the load, nor would you want it to be that, but it can be bigger. And in theory, you could use a 2 megawatt generator on a 1 kilowatt load, and that would not violate the code in any way. And we usually say that this is not a code provision, but we usually say that we don't want the load on a generator to be higher than 80%. That's not because the generator can't carry the load. It's to provide you some ability to do motor starts, some ability for future growth, some ability to have wet stacking on a diesel when the diesel won't necessarily pull full power. If you get a little bit of wet stacking, and you get wet stacking when you run diesel generators at very low loads, for longer periods of time. And so we like to not go over 80%. It just is a good rule of thumb that keeps us from getting ourselves in trouble. But that's not NEC. NEC only says that you have to carry the load and you can oversize it as much as you'd like.
What are the different people or job titles that could be in AHJ?
Brett, there's a great question. So many times the AHJ is typically going to be the guy that comes on site and looks at that generator and signs off on it. So typically I would say the AHJ is going to be your electrical inspector, but because it's got an engine in there and because there are fire limitations and so on, and fuel could make a difference to that, the AHJ could very well be the fire marshal. And particularly if you're designing something and you say, hey, I want to know if natural gas is okay. Well, that would be a fire marshal question. Both of those people are your typical AHJs. In a small city or county or whatever, it could be that they may designate someone else, but he's typically always going to have the title of inspector or fire marshal. And I don't think there would be anybody else that would have a different title.
Are there any common mistakes you see made in specifications when it comes to conflicting with the NEC, and how would you fix those specifications?
Yeah, great. Another great question. Yeah, we see a lot of specifications that have conflicts in the NEC. The biggest problem we have with conflicts has nothing to do with specs. It has to do with people speccing indoor generators, and we find code violations in the installation of those generators. But that isn't really a specification violation. What I would, it's kind of tough. Writing a spec is not a simple thing, but I guess I would think of two things. First of all, read the spec. We find some engineers go out, they grab a boilerplate spec, they copy and paste, and in it goes. And they don't even read the spec. They just figure, oh, this is our generator spec. And you look through it, and it'll have some paragraphs in here that refer to natural gas and some that refer to diesel, and you don't know what to do. For instance, if it's an emergency generator, then in that generator, you have to specify that it's an emergency generator. You have to specify that it's got an NFPA 110 controller. You have to specify that it have a permanent magnet alternator. You got to specify maybe that it has an LSI breaker. You got to specify that it have a remote annunciator and an emergency stop and so on. So you kind of have to know a little bit about this in order to make sure that your spec's okay. One other thing that you can, well, two things you can do, but they're related, is you, like our sizing program, if you use our sizing program, after you size the generator, it has a way where you can download a typical spec. And then you can just go through that spec and read it and make sure that it says what you want it to. And in many cases, it'll have some choices in there that you need to make a choice. The last thing to do, which we would recommend, is call somebody you trust in the generator industry. We think that we would be a good choice for that, and say, hey, I've got a spec and it's for this generator. Would you mind taking a look at it and letting me know if there's anything in there that I've missed? We do that all the time, and so we're happy to do that.
Great. Looks like that's all the questions we have. So we'd like to thank everyone for joining us today, and we look forward to seeing you in future webinars.